everybody. I have a question that was posed to me last night via text that is a classic. It's been around for some time. And this was even discussed in one of my classes many years ago where a student brought it up or I brought it up. I don't remember which because it's been many years. And this is an SAT question from 1982. I couldn't remember the year until I looked it up last night. And it's basically, given a radius of a circle is 1/3 the radius of a circle B. So you have two circles here with a sim ratio of 1:3. And we roll this small circle around the big circle. How many times does it revolve? Now, one of the things about mathematics is we got to make sure our definitions are good. The definition of revolving can mean different things for different people if we just leave it ambiguous. But for the most part is you're rolling this thing around the circle. It's spinning. Circle A is spinning. Circle B stays stationary. So we're from a perspective of an outside observer. So the problem with this SAT question was that it was incorrect. It was bad. And I looked it up online and some students wrote in and sure enough, the SAT acknowledged their mistake and rescored the question. But most people picked 3 because it seemed like a very obvious answer. And I'll show you why. So when we're dealing with rotation, you're thinking, oh, we're just going to compare the perimeters of the circles, which is, C is equal to 2 pi r. I haven't used my writing pad in ages. So given the ratio 1:3, the circumference of this little circle, call this circle A, is nothing more than 2 pi times 1, which is equal to 2 pi. And the big circle, of course, is going to be 6 pi, because 2 times 3 is 6. So we're going to have 6 pi as the circumference here. And you think, okay, well, 2 pi goes into 6 pi 3 times. Check, move on, next question, because the SAT is designed to be, 20 seconds, 30 seconds a question sometimes. Well, not so fast. And one of the things is that one reason why people did this is because here is a straight line. And let's just call this, 6 pi in length. And so I subdivided and did a ratio of 3. So we have 1, 2, 3. So it goes on 3 times in a thing. But that's not what's going on here. And I'm trying to remember our conversation. This was many years ago in my geometry class. And I pretty much did a distance rate time problem because I think we're talking about tangential versus angular velocities at the time as well. And that's how I approached this problem, if I remember right. But let's take a look at this. And another thing, and I don't think I brought this up when I talked about it, but when I got to thinking about it last night, let's take a look at radians. So radians is basically for one radius. Let's just call this 1, or let's just call this 3, because the radius is 3. That means this distance right here will also be 3. But when you're rotating a circle around this arc of 3 units, this circle is going to travel a little bit more because look at this. It's going to travel this way. It's going to be an arc. It's going to travel along this path. So this right here is bigger than 3. I don't know what it's going to be, 3.7, something like that. It's going to be a bit bigger. I can actually calculate it if I wanted to. Actually, it's going to be 4. I don't even know why I said 3.7. It's going to be 4. So this length is going to be 4. Because if we have a radius of 3 and a radius of 1, the radian is going to be 4. This is a 4 radian. That's going to be a 4 radian. Well, we have this object traveling this distance in the same amount of time as the angular. So the angle doesn't change. Call this theta. This angle does not change. But this distance here and this distance here, the tangential or velocity is going to be quite a bit different. So this one has to travel a little bit faster, the inside here. And it's the merry-go problem that many geometry students see. You're riding on, one person's riding on this part of the merry-go-round, one person's on the outer side. The angular velocity is the same, but this person has to travel a little bit faster. So that's kind of what's happening here. So this distance is a little bit further along. And when you have distance is equal to rate times time, and you're solving for t, So t is equal to d over r. So we need to find the distance, and we're going to have our rate, and we'll come up with the time. So basically it's this. This whole thing, this circle, the center of the circle is going to, I cannot draw a circle. Oh, good grief, that's ridiculous. I'm going to erase it. Where's my eraser? I downloaded a new version of Smartboard, and I got another 90-day free trial. So this one is not as good as the old one, believe it or not. I don't want a triangle. I want a circle. Circle. It's going to travel around this circle. Well, this circle circumference is, guess what? This is a radius of 4. So it's going 2 pi r, so it's going to be 8 pi. And this is 2 pi. Well, guess how many times 2 pi goes into 8 pi? You're just going to have 8 pi divided by 2 pi. And that gives us a formula. We're going to have the formula of circle 1. Oh, I labeled it A and B backwards. So you're going to have circle 1 plus circle 2 over the circle 2 is going to equal to the number of rotations you're going to have plus 1. Because it's going to be 4 pi. Normally you would have thought it would have been 3. I mean 4 times around. It's actually going to be just 4 times around instead of 3. So that's one way to look at it. And it holds true for many other instances. And this is why this is such a fascinating problem, because it's a good way to open up discussions about tangential velocities, circular velocities. In fact, my favorite way to look at it is, oh yeah, I forgot I was going to do this. I was going to talk about this. Is that there's a bunch of other things going on. And you can start comparing unlike items. Like let's take this square with a radius of 1. Nope, let's say side of 1 and side of 1. These two sides are equal. That means this radius is root 2 over 2. So remember, a radius of a polygon is from the center to the vertex. So that's just root 2 over 2. And that would put this radius right here. I can't draw worth anything. I can grab my handy dandy calculator, but it's not going to be 3 root 2 over 2. Okay, it's not going to be 1 to 3 ratio or 3 to 1 ratio. It's going to be, here, let me type this in the calculator real quick. This is a dodecagon, double a hexagon. The radius is going to be 1.972. Okay. And of course, root 2 over 2 is going to be what, 0.707. You should know that from your trig if you've taken trig already. So that's going to be 0.707, and that's not a 3 to 1 ratio. It just doesn't quite work. Okay. So, but you do get rotating the square around 3 times, because you take this side right here. It's going to pop up 1, 2, 3, 4. It'll pop over here. 1, 2, 3, 4. Pop up here, and 1, 2, 3, 4 pops up back again. But what about a triangle and a circle? So a triangle and a circle is very fascinating. So we rotate this circle around, imagine it spinning, but it takes this turn. Now, the exterior angle theorem is that the exterior angle is equal to the sum of 2 remote interior angles. So this angle and this angle, this is an equilateral, 60 and 60. So the exterior angle is going to be, well, this one right here is 120 degrees. This is going to make a 120 degree turn. And it's going to make another 120 degree turn here, and it's going to make another 120 degree turn up here to get back to where it was. That's 360 degrees. That is one extra rotation. So guess what? The perimeter of the triangle plus the perimeter of the circle divided by the perimeter of the circle is going to equal to n plus 1. So that formula still works. What if we did introduction to limits? And this is how I introduce limits in geometry. I usually start off with a hexagon and work my way up into a dodecagon, then all those weird numbers, 20-sided, 40-sided, 50-sided. We start getting infinitely small sides. And it's really, really cool how we can start approaching this formula via limits. Now, I am not good at calculus anymore, and which is ironic because that was my main focus in college. I did a lot of calculus in college and some proof-based courses, but I can't remember that. We're talking so many years ago. So this is a good way if you're teaching a calculus class. This is a good way to maybe discuss limits. So I copied this from a website, Stack Exchange. I never even heard of it before. And this is where they talk about this problem. Like I said, this problem is very, very famous. I knew about this problem years ago. And it's always fascinating because you could do this with 2 quarters. You get 2 quarters, the exact same circumference, and you rotate one about the other. It's going to take 2 rotations. Okay, again, depends how we define rotation, but it's going to take 2 rotations to come around it, even though the circumference ratio is 1 to 1. So it's still the n plus 1. And that's what we're going to have here. Now, this is the way I approached this problem originally. This is what my brain went to right off the bat last night. Is we're taking tangential velocities here. And this circle is traveling the same speed as its rotation. And in order to make that happen, it has to do 1 extra rotation to make it all the way around. And this is the calculus one. So if you're a calculus teacher, have fun with this because I looked at it for 30 minutes. I'm going, I kind of understand, but not really. Again, I haven't worked calculus and, well, I was much younger. So if you're in an AP calculus class, this was probably a lot of fun to do, to tell you the truth. So that is pretty much it. Going back here, you have this general formula that you can have right here. Okay. That works for any regular, well, I wonder if it works for irregular polygons. Probably not concave, just convex. I don't know. That's a question to investigate, actually. But this is one way to look at it. You're doing the perimeter or the circumference of the circle that passes through the center of the small circle. So that's the key to this problem. So my favorite web person for math is Mind Your Decisions. He has really, really great problems and he explains them very, very well. And he does have this problem on there, but he just shows the cutout, which is probably what most everybody's doing. But this problem is in his book, The Math Puzzles Vol 2, and it's right now for Kindle Unlimited. It doesn't cost anything. So if you have a Kindle Fire, definitely something to check out. So that is it for this problem. I'm going to go ahead and get this recorded and posted. Okie dokie.